Hey students, welcome back. This is our last video from Unit 7 or the gas laws unit. This one's going to be on the ideal gas law. So we have our bell ringer right here. This is from 7.5, so if you need it, go ahead and hit pause and meet us down below. Okay, so the ideal gas law, like I said, our last little bit from this unit, ideal gas law. What ideal gas law does is it brings all the variables. Wow, I can't spell brings. Let's try that again. Brings all the variables together. We've been working with these variables for a couple weeks now together into one formula. So we've actually seen some of these formulas as well, or some of these variables. So our formula, this is a big one, PV equals nRT. This is kind of where they all stem from. This is what comes from the KMT, kinetic molecular theory. This is what was developed from KMT. This is all our empirical gas laws coming together. It's like a culmination of everything. So there are some specific things that we have to use, some specific labels, if you will. So we've got P, which is pressure. All right, and we have two choices on pressure. We can either use 0.0821. All right, or excuse me, that's R in just a second. We can use, for pressure, we can use ATM or KPA. We have two choices there. Either atmospheres or KPA, your choice, and we'll talk about what that choice is and why a little bit down here on R. So V is our volume. This has to be in liters. You only have one choice. It has to be in liters. All right. N is moles. And obviously we have to be in moles. So sometimes we're going to have to convert from grams to moles, right? And remember, we do that by dividing by molar mass, right? And sometimes at the end of a problem, we'll need to go back to grams, right? And so we do that by multiplying by molar mass. So just kind of a quick review there. All right. R is that special one. We have not seen R before. We've seen all the other variables. R is new. R is a constant. This is called our gas constant. All right, and it's what brings all this together. So if we use ATM, the gas constant that we use is 0.0821. All right. Or if we have KPA, we're going to use 8.314. So you have two choices and it's dependent on your label on pressure. Okay. T is our temperature. And again, it still has to be in Kelvin. We still have to be in Kelvin. All right. So that should hopefully help us. Let's see what we got here for our examples. So we have a sample of hydrogen gas, has a volume of 8.56 liters. It has a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. We are calculating moles, and then we're going to calculate grams. So we're going to kind of hit both of these. We've got two things that we have to do. We're looking for moles first, and then we're going to convert it to grams. So let's go ahead and plug in what we know. We know we have a pressure of 1.5 atm. We have a volume of 8.56 liters. We have moles, that's our question mark. R, now since we have ATM, we're going to use 0.0821 because that's the label that goes, or that's the constant that we use on atmospheres. T is our temperature, and it's degrees C, or 0 degrees C. Got a little ahead of myself, 0 degrees C. And so we add 273.15 to that. So it's 273.15. Now we're ready to plug it in. Let's kind of see what this looks like. So remember our formula is PV equals nRT. P 1.5, V 8.56. N is what we're looking for. R is 0.0821. And our T is 273.15. Okay, now to get N by itself, we're going to divide each side by 0.0821. Blow this up a little bit, 0.0821 on each side. Divide by N by 273.15. Those cancel out. Do that same thing on the other side. Divide by 0.0821 and divide by 273.15. Okay, so our N is going to be equal to 1.5 times 8.56 divided by 0.0821 times 273.15. All right, so let's go ahead and plug that in the calculator. 1.5 times 8.56 divided by 0.0821 divided by 273.15. And we get 0.57, and this is going to be moles. Label on this as moles of H2. So that's our first step. First step says to find moles. But it also asks us to take that to grams. So to get to grams, we multiply, we kind of said that up here, multiply by molar mass. So if we kind of slide this over, give ourselves a little more room, and a new color, we have 0.57 moles of H2, and we want to convert that to grams. H2, we take 2 times 1.00794. All right, 1.00794 was found on the periodic table. And that should give us 2.02 when we do our math for molar mass. All right, so we'll put 1 mole of H2 on bottom and 2.02 on top. And so we'll take that times 0.57 and we get 1.15 grams of H2. So that's one way that we can do it. All right, take a second, soak that in. All right, let's look at that next one there. All right. Ooh, this time we've got grams, which we can get to moles, right? But we have to do some work, right? We have a volume, so that's V. We have a pressure. We're looking for degree C, then we've got to take it to degrees, or excuse me, we're looking for K, and then we got to take it to degrees C. So our pressure was 1.00 atm, or atmospheric pressure. V was a big giant number, 2.7 times 10 to the 6, so that's 270, well, 2,700,000 liters in. This is where we're going to start, right? If we start here, we know we have 1.10, but let's put that in out of scientific notation. We have that many grams of helium. Okay. So I can get to moles by dividing by the molar mass of helium. All right. This will tell us how many moles of helium I have. Let's make that just a little smaller. All right. So we're going to take 110,000 divided by 4, and we're going to get 27,500 moles of helium. All right. R is our gas constant. We're at ATM, so we're going to use 0.0821. And T, our temperature, that's what we're looking for. That's our question mark. Okay, so let's get ready to plug all this in. We know PV equals nRT. Our P is 1. We got a big, huge number for volume, 2,700,000. Our N is 27,500. Our R, 0.0821. And we're looking for our T. Okay, so to get our T by itself, we divide each side by 27,500 and 0.0821. So divide each side by 27,500 and 0.0821. It's a terrible 8, but I think we get the picture. So T, these cancel, is equal to 2,700,000 divided by 27,500 and 0.0821. So let's plug that in. We get 1,195.88. That's Kelvin. That's our answer in Kelvin. All right, and now to go to Celsius, all we have to do is subtract 273.15, and we get 922.73 degrees Celsius. Kind of warm up there. All right. Thank you. See you next time.